So I just have a few brief comments before we get back into more quantum algorithms. Okay. All right. So today we'll continue discussing algorithms. We've introduced the Deutsch-Josa algorithm last time. We'll try to see if we can code it in Qiskit. And then we will do Simon's problem. I'll introduce the theory of Simon's problem, which is very similar to the actual Shor's algorithm, which is, of course, the famous one that allows you to factor numbers faster than a classical algorithm. But first, a few important notes. Okay, so our quiz 2 will be next week, April 5th. Covers the material on the tutorial that you have all just completed and that you have done, submitted the homework. I know some of you did not see the assignment, so I've extended the due date for it. And you can submit that, and then as soon as that's submitted, then I'll release the solutions to the tutorial as well. So you'll have the solutions before the exam. Okay, and then the next one is basically the final quiz of the semester. It will be on the very last class of the semester. We'll cover some of the remaining things that we could not cover in the first two quizzes, like quantum circuits, a little bit of algorithms. Obviously, it's hard to do algorithms in an exam or quiz setting, and entanglement. And hopefully, we'll have some time to talk about entanglement before the end of the semester. So the next thing is, of course, that there was a term project that is part of this course. And to explore quantum algorithms, as I said, I think some of this will depend on how far we get in the course with the algorithms. So it may be that some of the algorithms that I don't quite get to, at least I might assign one or two of them also as final projects. But anyway, the idea is, I think there are 30 students in the class, so 3 students per team, because that'll probably make it easier for you as well as to work together. So you can form teams. 3 students per team are allowed, and the team list and project selection list will be posted on Canvas. So I'll put like a table, and you can all sign up with your teams and your projects on Canvas. And yes, and finally, there's no other exam beyond these 2 more quizzes and the final. Any questions on this?
Questions to be on the exam.
Which one? Quiz 2?
On the 5th.
On the quiz 2?
Yeah.
Oh, I think roughly the same as the last time. Like I think 7 or 8, I guess, was it last time?
Because the tutorial has about 60.
Huh?
The tutorial has about 60.
60 questions? Yeah. It's a long one. No, it won't be that. Okay. Here's a partial list of suggested projects, but I mean, some of these obviously get more and more advanced. But I'll put these up also in the list in the Canvas, so you can look at them. So yeah, there's a whole bunch of projects that we could do. There's also just things like exploring, and I'll just put it out there, like even like when we do like a problem in the class, I might show you like a simpler version or like a more simplified way to like just get to the final, function or circuit. And it's, I'll give an example, like for example, with Simon's problem, we will just import an oracle that has been written for us by Qiskit. So just implementing an oracle that does it on your own, I'm just throwing out that could be also at least part of another project For example, implementing more generalized oracles and things like that. But this is like, if you're ambitious, you can try many of these as well, right? Or any of these as well, along with some of these. So I'll put a more detailed list, but this definitely, and I mean, some of them are already well established, and there's plenty out there on the web for you to look at in terms of the circuits and then of course once you have the circuit, then you just follow our template, put it into into the quantum composer and implement it, and that'll be fine. That's enough to finish the project. You should explain it obviously in your code and your and in a little document, like I've said before, that you need to submit along with the code. You need to submit a document, which I'll also put in the assignment. So yeah, that explains how the algorithm works. So so there's a lot, and we can talk about it. Like if you have questions, we can go over some of this either in office hours, or you can just make an appointment to come talk to me about which problem you would like to try. Okay, so yeah, if you look up on IBM's website, they have a lot of information about each of these topics as well, and some of it is outside of that. Like some things like quantum games and things, that's kind of, I think, interesting and cool, but probably a bit challenging. So those would be the more reach projects, I would say. Okay. So any other questions about the projects and the quizzes? Okay. If not, let me just briefly remind you that in the last class, we discussed the Deutsch Jozsa problem. We discussed the Deutsch problem, which is just for like 1 bit. Basically we had just 1 bit on the input. So n equals 1 over here was the Deutsch problem. The Deutsch Jozsa problem is for an n-bit string, so a function f that takes n-bit string and maps it to a single output thing. Okay. And as we've talked, I mean, these functions need not be silly, right? I mean, even for the 1-bit case, we gave an example of like a very complicated function, find some expansion of some number with x as the input. Now, obviously, if you add n-bit strings, now you can see that the sort of the universe of problems for which this function could be useful is bigger. But of course, the property of the function that we are trying to look at is very sort of simplified here. All we want to know is the property of this function is whether it, you can think of it as dividing all the functions into a bucket, right? So there's one bucket, which is the constant functions, which means the output is always either zeros or ones, right? And the other is when it is balanced, which means, as we have discussed, that there'll be an equal number of zeros and ones on the output. So that is the oracle, and as we saw, that what it does, this quantum oracle, is basically it takes the input x, and then the output, which of course is just going to be 1 bit, is basically taking this output register y and adding this function f of x to that output register y. And that's the output over here. And in the last class, we saw that by carrying out this circuit, and this circuit I want to emphasize, it follows this paradigm that we have said will be very useful in quantum computing, which is to first rotate with Hadamard's, right? So Hadamard rotates. So this part is rotation, the first part. The next part is compute. Compute is carried out by any number of different unitary gates. It could be done with an oracle. It could be done by some other circuit that you could create, like quantum Fourier transform, etc. So we'll come to those examples in a little bit. But essentially, this part is sort of the part that does the computations that you need for your function that you're trying to calculate. And then the last part is again rotate back. Okay, so it's like rotate, compute, rotate. This is the paradigm. This is what Simon realized, and he kind of made this famous, this paradigm of quantum computing, that it's always something like a rotation, computation, and a rotation back, and then of course followed eventually by measurement. Okay. So that is our paradigm, and that's outlined here in this circuit. And we can now implement this circuit in Qiskit. But before I do that, any questions about the Deutsch problem or the Deutsch-Jozsa problem here? Okay, so let us okay. Stop the share of this PowerPoint. Anymore. Yeah. Zoom folks, what are you seeing? Do you see desktop?
Yeah, I see your browser.
Okay, good. Finally. Okay. All right, very good. And you still see my browser? Just expanded, I hope?
Yeah.
Okay, very good. Let's make this bigger. Oh, no. Okay, everybody still seeing people here in the audience? You can view this. Okay, so this is the Deutsch-Jozsa notebook. And yeah, I know I didn't share this because, of course, the problem is that every time I seem to share it, it seems to break. So I had to come up with a way to share this with you all ahead of the class. Okay, but for now, hopefully you can type along with me if you need to, or later on I'll try to post it on Canvas so that you can just copy it into your notebook. So for now, I mean, it's not super important to follow everything. I just want to show you the basic steps of how we create the circuits, how we then carry out the computation. All right, so in this first part, here is the usual imports of the Qiskit, IBM Q, AER, etc. that we have all seen before. Import the quantum circuit as well. And then at the end, we'll visualize plot histogram. So we'll use that. As I said, I've had very bad luck with this plot block multivector. Every time I execute it, it works sometimes, and then sometimes it doesn't work. And that's really frustrating to me. I have a ticket and I don't know. It's something that I'll have to sort out with IBM eventually. But yeah, this part, the other parts seem to generally work, like especially plotting the histogram and all that seems okay. All right. So as I said, we're going to do a multi-qubit Deutsch problem, right? I mean, we want n-bit string. So for our purposes, we'll just do 3 bits because at least that gives us a reasonable space without making the circuits too long to sort of represent easily. So the first one we want to do is create a quantum oracle. And this quantum oracle is just the constant oracle, right? Okay, so, and the idea is that we are going to randomly decide whether the outputs are all zeros or all ones, okay? Or 0 or 1 here, okay, in this case, because it doesn't matter, we just know that the output is going to be 0 or 1 independent of what x the inputs are. Okay, that's what a constant function does. So that's easy enough. We initialize the constant oracle as a circuit with n plus 1 because, of course, that's n input registers and then the 1 output register over here. Okay, so n plus 1. And then, as I said, we randomly decide whether the output should be 0 or 1. If the output is 1, then we want to flip the bit, right? Because normally Q3, the quantum bit starts in the state 0. So we randomly decide whether it will be flipped or not flipped. Okay. In this case, it ended up being flipped. So it gives you an X over there, and then that draws. So this is our first oracle. Just randomly decides whether the output is 0 or 1. Okay, so far? So now, again, you don't have to use this code. As I mentioned, you can just simply look at the circuit. You want to go back to Quantum Composer and do this. But you can start to see if you have many qubits, it starts to get a little bit difficult to do it by hand in Quantum Composer. But for 3 qubits, it's still quite manageable. You can do it by hand. So you don't have to use this Python code if you're not familiar or you don't want to deal with it. All right, now let's create the balance oracle. This is a little bit more interesting, right? Because it has to be balanced. So let's think about like, if I wanted a balanced oracle, and before I show you the code, let's talk about what that might be for 3-bit strings. Okay. So here is one. I mean, you can come up with as many different balance functions as you like. Well, within the space of eight numbers, right? You have 8 numbers, 0, 0, 0 up to 1, 1, 1. And then so you can just choose. Let's say I choose some function such that it divides up the 0, 0, 0 to 1, 1, 1 into 2 buckets, right? And the inputs that give 0. That's inputs that give 0 output. So output is 0 is on this side, and outputs that are 1 are on this side. And there are 8 possible numbers, so just divide them up half into each side, right? That's all you have to do. So what we can choose to do, for example, is we could say, well, if there's more than 1 bit that is 1, then I will call that a balanced function. I mean, it'll give me a 1. And if there's only 1, or if there's an even number of bits, let's say, or something like that, well, there are 3 bits here. So okay, I'm just going to randomly put something. Okay. So let's say 0, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 0, 0. Okay. So let's just choose that all of these will give me an output 0, and then anything that has 2 1s in it, right? So 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1, or 2 or more bits will all give me 1s on the output. Just as an example of what a balanced function could look like. Okay. So we've just chosen this randomly, right? So that's exactly what we'll do in the code as well. Is we'll base it a little bit more than just random. We'll allow the user to select different balanced oracles that they want. Okay, and they can do that by specifying a bit string. Okay, so how many balanced oracles can there be? What do you think? Okay, we know there are 2 constant oracles, the ones that give you either zeros or 1s. So how many balanced oracles can there be? If we have 3-bit strings, so there are a total of 8, 8 strings as inputs. So what do you think? How many balanced oracles can we get? Yes?
I could guess 8, choose 4.
Yes, very good, exactly. So we just have to pick 4 groups, and whichever way it is, it doesn't matter. So how many ways can we divide up 8 strings into into four strings on one side, four strings on the other side. Okay. So that's all there is to it. Okay. Okay, so as I just mentioned, we'll allow the user to pick, some representation. In this case, it's a string with some bits in it. Okay, 101, as I just picked here. Okay, and so you can play around with this, right? So in your code, when you write this, you can see what happens. And the idea is that if the bit string is 1, then that will flip the input qubit. Okay. So let's look at that. So it flips that qubit, right? And then it'll carry out the operation such that it'll produce a 0 or 1 on the output. Okay. We'll see this in just a minute. Okay. That is over here. Okay, so maybe we can work this out in this case. Okay, let's work out this case. So what I'm trying to say here is that if Q0 is 0, forget the x's for a second, right? If Q0 is 0, then it does nothing to the last register, which means the register stays as 0, okay, which is the output register. But if it is 1, then it flips it. Okay. So in this case, you can see that when these two are 1, it'll flip it. Okay. And then if this one, but this one is not 1, right? Because it's always going to be 0. It is not being flipped by this oracle. Okay. So you can see it's 1, 0, 1. It follows that pattern. That's where that 1, 0, 1 comes from. Okay. It's saying I'm going to choose Q0 to flip the output qubit. Obviously, if I have 3 plus signs here and only two of them are flipped in the input string, then you can see that gives me definite either it'll produce 2 buckets basically. We'll have like any 2 of these. If they are ones, that will flip the output, and if not, it will not flip the output. Because there are a total of 3 plus signs here. Remember, this is XOR addition. So if you add something to itself, it's going to give me back the original. Okay. So maybe if you want, we can go through an example. That might help. Okay. Then we have the C naught gate. Okay, so now we can see for which classes of input strings the output will be 0, and which classes of input strings the output will be 1. So it's just basically a truth table, right? So we need all the input strings that are possible. Oh, 0 space. I have to tighten up these last three. Far too generous. Okay. So we can work through the pattern now. Right? So it's 0, 0, 1, right? So sorry, 0, 0, 0. That's the first reading from remember that the pattern is always from the top down is right to left. So that's 0, 0, 0. And we can see that will flip this one to 1, 0, 1, right? That's what that 1, 0, 1 represents. And now we see what happens in the control NOT gates. Okay. So the first control NOT gate makes this into the 1 state, right? The next control NOT gate does nothing because this control qubit is in the 0 state, and the last one flips it to 1 again. It flips this qubit back to 0. Okay. So we see that 0, 0, 0s will end up with a 0 over here. Okay. What about 0, 0, 1? So now the input over here, if this is now 0, 0, 1, is the number that's coming in here, then the output here is 1, 0, 0. And so now you can see that because there's only one of these controls that is 1, okay, and the others are all 0, we see that this will produce a 1 on the output. Okay. And you can start to see the pattern again. 0, 1, 0 is the same. Let's see if what that will produce. Okay. Now this has flipped. That's a 1. This is 1. And this is also 1. Okay. So now we have 3 control knots. So what is it going to give me? With 3 1s coming in. Yes?
Yeah, 1.
1. What about 0, 1, 1? Why don't you work this out and tell me? So now I have 0, 1, 1. I just have to change the input. So 1, 1, 0. So that's 0, 1, 1. What now? Yes.
0.
Okay, so we're beginning to see that this breaks it up into a slightly different bucket than the one I wrote down here. But it is going to give me a similar pattern, that there's going to be some that are mapped into zeros, some that are mapped into ones. Hopefully they're balanced, right? So what about 1, 0, 0? One or 0? There's only 2. Yes.
1.
1. Okay. Well, all right. You can work out the rest. Yeah. You have the pattern. Everybody okay with that? See what the pattern is here. Yeah, definitely with ones, even number of ones or zeros so far has produced a 0. Odd number of ones seems to have produced ones, right? So my guess will be the next one is also 0. So the next one, and then the last one probably is coming in here. That's just a guess. Okay, but that's probably. So, and you can play around with the input string and see what happens for different input strings on the output. Okay. And yeah, so we have this as the so that does the control NOT gates. And we just, this barrier, by the way, is just to like separate things up. It doesn't mean anything. It's just something we put in to like make it easier to see the differences between the different parts of the circuit. Okay, and then at the end, we have to flip everything back. Okay, so we put the balanced oracle again with X gates. Okay, that would, if nothing else were to change, that would bring all these input qubits back to 0, 0, 0. Okay, so that is why an oracle basically does nothing to the inputs, and then at the output, it adds Y plus f of x. Y, of course, in this case, the input register is always in the state 0. So therefore, the output register is always f of x, where x is the input string. Okay. So that is our balanced oracle. So now we are finally ready. This is the oracle. This is that U in that circuit that I drew on the PowerPoint, right? That I showed you and that we discussed last time as well. So this whole thing here is that U, because we had to implement that also in the quantum computer. So this is what this circuit implements that oracle in the quantum. And now we have to actually implement the Dutt-Jozsa algorithm, which of course, as you remember, what's the paradigm I told you? What do we do first? When we want to do the Dutt problem or Dutt-Jozsa algorithm, what's the first step in quantum algorithm? Yes.
Initialize the qubits.
Yes, but we can assume that all the qubits are at 0 to begin with. What's the next part of the Dutt algorithm or the paradigm that I just talked to you about? Quantum computing. Rotate. Very good. What does rotation mean for us usually? What operator or gate can we use to rotate? Yes, Hadamard. Excellent. So we need to implement the n-bit Hadamard, which is straightforward again. So for every qubit in the list, in the range 3, 0 to 3, we basically put the Hadamard. So we just take the quantum circuit as defined here and create Hadamards on all the qubits right here. Okay. And there is one thing, which is that the last qubit, the Q3 over here, if you, sorry, I should have kept the slide, but if you look back at the Dutt-Jozsa algorithm, it said that the input register had to be in the state 1, not 0. Okay, sorry, the output register, not the input register. This output register, remember Q3 is the output register, has to be in the state 1 when it starts and not 0, which is easy enough. We started in the state 0 and then apply an X gate to make it into the state. Okay, so this is the Dutt-Jozsa algorithm, which is rotate. We rotate everything, right? But we basically have to apply the X gate just to the state Q3, because that is what is expected in the Dutt problem that you're going to start with. Okay, all right. Oh, sorry. Once we've done that, now we can apply the sorry, that is the oracle. Now, okay, and of course we have 3 bits for storing the output of the measurements, and now we can just so this is an important maybe operator, the compose operator. Okay, so what the compose operator does is it takes this circuit and composes it basically like the circuit composer with the earlier balanced oracle circuit that you had already done. Okay. If I had been more careful and if I had originally, we could even do just plus sign. But the problem is that this quantum circuit has 4 qubits, which is fine. That is exactly what that one also has, 4 qubits, the balanced oracle. But this one has extra classical registers. Okay, because of course we want the classical registers to store the output of our input register. Basically, at the end, we measure the input register. Remember, in the Deutsch problem, at the very end of the algorithm, we measure the input register and we discard the output register. But we need to store that results of the measurement. So when I made this circuit, I added in the classical register here. That means that this circuit is not compatible directly with the other quantum circuit, the balanced oracle here. Okay. If I had wanted to be more clever, I could have started with the balanced oracle. I could have made three output registers, classical registers, which are these represented by the C3 with this dash, which means there are multiple registers, three of them. Okay, three classical bits basically. So if I had started like that and written the balanced oracle like that, I could have even just done DJ circuit plus. It allows you to do plus, which is just saying take this circuit and join them. But that only works if both circuits have same number of qubits and classical bits. But if it doesn't, then you use the compose operator or compose function, I guess, method on the DJ circuit as shown here, and add in the function, which is in this case the balanced oracle circuit. You just add it to this, and then the compose knows that it needs to just put them together, stitch them together. And it knows how to handle classical registers and all that when the other one doesn't have classical registers. In fact, you can do this with quantum registers also. Like you can have circuits with unequal number of qubits, and you can specify which qubit should control which other qubit in that other circuit and so on. So obviously there's a lot of documentation that you can go into about all this. I'm not getting into it. But okay, so this is finally our Deutsch-Josa circuit. Okay, we rotate over here. The X is just to convert Q3 to the one state. We rotate here, so that's including this Hadamard. Then we apply the oracle, which is the U part of our Deutsch-Josa algorithm, and the oracle, puts everything back at the end for the X state, for the X register, brings it back to its original state, and then for the Y registers, this is the Y here is just a single qubit. That will be the output register over here. And then at the end, of course, we want to measure just the input register. We don't care about the output register, we throw it away. Okay. But this brings us to, and we have to do, of course, rotate again, right? We haven't rotated yet. So we need to rotate back, as I said. So we rotated, applied the computation, and now we need to rotate back and measure. Okay. So let's go through the rotation part. Now, again, I apply the Hadamards, right? I apply Hadamards for all the qubits. And again, I just draw a barrier to show that that's a separate operation. And then finally, I do measurement. Okay. So measure I to I. Input qubit registers to output classical register. Okay. That gives us this circuit. And of course, you're welcome, if you don't want to worry about all the code, just to go into Circuit Composer, and you can just make this circuit yourself, this final circuit. But the Qiskit allows you to compose circuits like this by code, which is nice. Okay. This is the Hadamards over here. Probably I should have put one more barrier here and then done the Hadamards. That would have been a little cleaner. Okay. So I didn't do that. You're welcome to clean it up and put a barrier in here, which you can do just by DJ circuit.barrier before the Hadamards. Okay. Then that'll make it very clean. It'll be like Hadamards, oracle, Hadamards again, measurement again. And that's it. That is our circuit for the Deutsch-Josa algorithm implemented on Qiskit. Again, I'm not going to send this to the quantum computer, but we can simulate it. Okay. And so I carry out the simulation. Oh, by the way, before I do the simulation, we know that this was constructed as a balanced function, right? It was a balanced oracle. Okay. So what do we expect on the output here is the question. Let's think about that for a second. Before we run the circuit, let's think about what should we get on the output. You may have to think back to the definition of how we work this out in the Deutsch problem last time. There were two classes, remember at the output, like we got either 0 plus 1, before we did the final Hadamard, it was either 0 plus 1 times some output on this last register, or 0 minus 1 times some output on this output register here. And we threw away the output register. See, the output register, we don't even measure it. We don't care what happens to it. So if the inputs are in, say, the state 0 plus 1, and I apply Hadamard, then what will the output be? If the input is in the 0 plus 1 state, and I apply a Hadamard, what will the measurement give me? Yes?
X.
If the input qubit, one of the input qubits is in the state 0 plus 1 over root 2, right? Because it's a qubit, then applying Hadamard brings me to which state? Not sure.
0, like 0 plus 1.
Over root 2, but that's the,
That's a plus.
yeah, 0 plus 1. Yeah, that's a plus state, exactly. So if I apply Hadamard to a plus state, what happens?
Z state.
Yeah, Z state. Which Z state though?
Because the
Which Z state? Plus will go to which Z state?
0.
0. Very good. Excellent. Exactly. So Hadamard applied to the plus state will give me 0. Hadamard applied to the minus state will give me 1, right? So in the Deutsch problem last time when we talked about it, we said that's the secret that basically leaves the input registers in the state plus if the function is a constant, and in the state minus if the function is balanced. If you don't remember, you can go back and look at our discussion last time of the balanced and constant functions and how it works. And so what we're expecting then at the output then, right, since we know it's a balanced function, is the state. What should be the state on the output here? What should be the measurement give me? Is it good? Yes?
1.
1 for all bits. So the output string should be 1, 1, 1. Remember, now there can be any number of states here, right? It goes from 0, 0, 0 up to 1, 1, 1. So we could get anything from 0, 0, 0 to 1, 1, 1 on the output for the probability distribution. But we are expecting, if everything works correctly, that the output should only be 1, 1, 1. Okay. Does that make sense to everyone? Okay. Then, or the other way to say it is that the probability of getting a 0, 0, 0 should be very small, should be 0. And of course, for all the other strings as well, there should, there are 8 other strings. There are a total of 8 strings, 0, 0, 0 to 1, 1, 1 that I could get on the output. And I'm expecting that none of them will be here on the input, on the final measurement. Okay. So, okay, that was the whole code. So let's go ahead and execute it. Okay. Okay, very good. And now this part here is just our template that I gave you before for how to run a circuit. It's just, I mean, I think I've already imported these, but I never remember if I've imported or not, so I imported anyway. So I execute the job and I monitor the job. Yeah, it does run, get the counts. Oh, it did print. So, okay, I see. Oh, and it executed it. Sorry, I thought those were two separate. I guess I put them all in the same. And okay, so we see there is one string that has all the probability in it. Let's hope that it's the right one. Oh, it is the right one. Okay. 1, 1, 1. Okay. So now, of course, I encourage you to play, for example, with the balanced oracle. Okay, construct some other balanced oracle of your own. Okay. For example, the one I used was 101. You can ask yourself, like, how do I make a balance oracle that does something else, which breaks up the bits into some other string, for example. Okay. And see if you can construct your own balanced oracle and then execute the Deutsch problem and see if it works. Okay. But first you need to make sure you did a balance oracle correctly. Other than that, it's the same steps. Okay, so any questions about this process and how the code is? So I'll post this again on Canvas, but as I said, I hope, otherwise I don't know what other way there is to share the file. I could put it on GitHub or something, I guess. I don't know that they let me directly share from IBM, because that would be the easiest thing. If I could just post this somehow to our group in the IBM lab, then you could just open it right there in IBM. Yeah. You have a question?
I have no idea. That's for set up my personal IBM thing. So I'll just ask after class.
Is what?
I'm not in the group, I think. I'll just ask after class.
Oh, really? Huh.
Cause my IBM ID is my personal email. And
Oh, that's the problem.
Yeah.
You need to create another one
Okay.
with the PIT ID. That's how you get the. So, okay, another thing, of course, I should mention is we ran this on the simulator, but I again encourage you to use the same, now I think it's actually maybe worth it to run the job, not just on the back end, which is the, where did I do it? Yeah, in class, March 22nd. Okay. So that, maybe we can do it now. Why not? Okay. So you see here, we imported the IBM queue and the providers, and we used one of the provider backends and executed the job on the provider. So now we can actually do that. Let's try that out and see if one of the providers that we can pick. And actually, there's a function called least busy that tells you which provider is the least busy at the moment. So you can actually import your, find out which one is least busy here, and then put it there. So I guess I should have called this guy Joseph. Okay. Let's see. Okay, we deprecated. You should use some other package. Okay, so we have all of these. Okay, I'll have to look this up. I don't remember which package it's in. Right. Okay, but for now, of course, we can just go back to the job. Dashboard. View resources. Save. For now, since we don't know which one is the least busy, it's fine. I'll just use what I used before. Now, it's actually going to send it to the backend IBM port. And this will obviously take longer. Nothing called circuit. That's because I called it DJs. Like Joseph. Okay, and we can also use the job monitor again. Job is queued. So, okay, so you'll have to check when this job gets completed here. And once it's done, you can then execute the same commands, basically this histogram, this part here, count equals jobs result dot get counts, and print and plot the histogram, and we'll see what it gives us. So this is the simulation. Let's see what it does when you actually run it on a real quantum. So I encourage you all to run this code. I'll share the code with you so that you have it. But I encourage you all to run it and see what results we get. Okay, so with that, let me start the IBM quantum stuff. Let's talk about a new algorithm. It's called Simon's algorithm. Before I do, I want to introduce a couple of circuit identities, which will turn out to be useful for a lot of the things that we do. So let me just introduce those. These are just purely, in a way, mathematical, but also they help us to visualize sometimes what a circuit is doing and why it works without having to always go through it step by step, for example. Okay, so let me start with first identity here. It's called the phase kickback identity. Yeah. Okay. As you've seen, in a lot of different cases, which they put handles on. So the basic idea of the phase kickback circuit is as follows. So normally when we take a gate like X, right, and we operate it on a state, X, for example, operating on 0 gives me 1, and X operating on 1 gives me 0 because it's a NOT gate. And if there is a superposition, for example, X acting on, or if I flip the state of X, right? So for example, if I operate in the plus state, right? So now this is plus, which is 0 plus 1, right? In this case, X acting on plus is 1 over root 2 of X acting on 0 plus X acting on 1. So that is just, again, because it flips 1 and 0, it does nothing. So basically it gives me plus. Okay, and X acting on minus, though, we have seen this before, right? I mean, is that it's X acting on 0 minus X acting on 1. So that gives you a minus sign. right? Because now this will go to 0, this will go to 1. So that looks like the minus state, except that there's an outside minus, because I had to pull out a minus sign to make it look like the minus state. So what I mean is there's a minus sign and then there's the minus state. So X acting on the minus state gives me back the minus state, but with an eigenvalue. Remember the word eigenvalue, which is that it pulls out a number. The number is +1 for the plus state and -1 for the minus state. So plus and minus are also eigenvalues or eigenstates of the X operator with the +1 and -1 eigenvalues. Okay. Which is, of course, why they are also called the plus X and minus X state, because they are exactly that. They give you that eigenvalue. Okay. But of course, as I said, this is a global phase, so it's unobservable. This -1 or +1 out here is unobservable. Okay. But now let's see what happens if I apply this to a superposition, but with like one more qubit as well in the mix. Okay. So let's talk about say the state, which is over here. Okay. And first I will apply Hadamard on this circuit over here. Okay. And on this one, I'll apply Hadamard first, and I may sometimes apply an X gate or not have an X. Okay. So this is optional. Let's put it that way. Okay. So when I don't have this X state here, this input state over here is ++. Everybody okay with that? Right. It's a ++ state coming in before the C0 gate. Okay. So if I have ++ and I apply the C0, and remember this is C0 now of the 0, 1, because it is the top qubit is the control qubit and the bottom qubit is the target qubit. Okay. All right. So how do we go about this? Well, okay. So before we do the full plus and plus, let's just do C0 0, 1 acting on plus with 0. Okay. So to write this, I write this out as 1/√2 C0 on plus on 0, 0 and C0 on 0, 1. Okay. 1, 0. Because the first one is in the state plus. Okay. Well, C0 0, 1, right? So that is the right qubit is controlling the left qubit. So it does nothing, right? Because in this case, the right qubit is always in the state 0. So it does nothing. So the output here is plus. Okay. And similarly, if I take C0 0, 1 acting on +1 now, right? That's the one that will presumably do something. This C0 0, 1 on 0, 1 plus C0 1. But this one is going to flip this to 1, 1, right? Because the 1 controls on that, creates a 1, 1, and this one will go to 1, 0. But again, that's identical to the initial state because there's no flipping of the phase, it's just the same state. So this also gives me +1. So we can see right away that C0 0, 1 acting on ++ is going to give me ++. Because plus plus is just plus 0 plus 1 over root 2, and C naught does not affect either of them. So the output state is C naught plus plus. Okay. Now we can do this also for minus. Let's do C naught minus minus. Or let's do C naught minus plus. Okay. That may be a little bit more interesting. Okay. So I'm just going to go straight up to, this next thing without any justification. Hopefully you can see what's going on. Sorry, again, I figure 1 minus 0 plus C naught acting on minus 1. So please don't be confused. When I put the minus here in the first, you can think of it like there's a comma in between. The minus is for the first qubit or the left qubit, and the zeros and ones are for the right qubit. Okay. Okay, so what does C naught do? Well, if this qubit is in the state 0, it does nothing to that state. So the output is 1 over root 2 of minus comma 0, right? But then when there is a 1 here, it acts with the X gate. So that's the X gate acting on minus comma 1. But we just saw that X gate acting on the minus state, okay? X gate acting on the minus state gives me a minus sign. Okay? So what does this do? Well, this gives me 1 over root 2 minus comma 0 plus minus comma minus. Minus sign of 1, which I can now write as just the state minus minus. Because X acting on the state minus comma 1 pulls out a minus sign. So this gives me the state minus minus. So why is this interesting? Well, what we see normally when we did, like, for example, the Bell state preparation and things like that, it was usually we put the control qubit into a superposition, and it was a target qubit that was affected, right? Because, so for example, in this case, when I put the control qubit into H, and if I don't do anything to the target qubit, I just apply the regular gate, which is just that C naught 0 1, the output here is the Bell state, 0 0 plus 1 1 over 2. Okay, because it's just, this is 0 plus 1 divided by root 2, and it'll flip this guy when it's in the 1 state, and we'll leave it untouched when it's in the 0 state. So the output is 0 0 plus 1 1 divided by root 2. Okay, so in this case, what I'm saying is that it took the phase, which is the plus state over here. Basically, this is what is coming out here, right? And effectively, what it did was it put the output into a superposition that depends on this input phase of the control qubit. But here in this circuit, what we have done by putting Hadamard's first on the inputs, on both the inputs, okay, and of course the X gate to that just decides whether the input is flipped or not. We can, so meaning if I put this X here, then instead of preparing plus state here, I prepare the minus state, right? Which is basically what this is here, the minus plus superposition, okay? So this is a product state, but after after the entire operation, it leaves the control qubit. Remember, the control qubit is the right qubit here. It changes the phase of that superposition, because when it initially started, this was plus, and just rewriting this a little bit more clearly, this is X, this is H, then this state is a minus state over here. But the control qubit has, the target qubit in this case has remained as minus as per that output, because that's the left state over here. But the right state has turned into a minus state. So this is what I mean by phase kickback. Okay, so if I don't put Hadamard's on both, if I put Hadamard say on one, then whatever phase is on the control qubit gets affected into the final state, which might be an entangled state in this case. But in this situation here, when I put a Hadamard on both the inputs, Hadamard for everything, for example, then the output affects, that is that the state of this target qubit actually maps back onto the control qubit. It affects the phase of the control qubit. So for example, at this point, if I now applied another Hadamard, okay, and I put another Hadamard over here, what will I get? I'll get 1 and 1. Okay, so I started with zeros on both inputs, okay, and I flipped them into the state 1, 1 at the output with this circuit over here. Okay. This is called phase kickback. And it's an often, you'll notice that this Hadamards followed by some C0 gate followed by Hadamards will appear frequently in all our sort of circuits. The point, I just want you to remember that now the minus state has been mapped back onto this. Because this is the input register in the Deutsch problem, right? The input register is this one, and it has been basically flipped to the 1 state by the action of the control non-gate. Okay. Without this control NOT gate, this guy would have remained in the state 0 normally, right? Or rather, without this Hadamard on the other qubit, it would have remained in the state 0. But the action of the Hadamard made that phase minus sign map onto this guy, and then that Hadamard flips it to the 1 state. All right, it's just an identity. I mean, there's no deeper meaning. I just want you to understand this because when we add up to like multiple registers, you see that this starts to like add up, so to speak. The minus signs sort of start to matter here. Okay, this minus sign here will appear many different places like this. Okay. Okay. So that's the phase kickback identity. And it all actually comes from an identity that we already proved in an earlier class, which is we said that the C0 acting on this state, that is going the other direction, that is C0 1 0 state, this guy is equal to we proved this result in some detail when we were looking at how to prove circuit identities in general. Okay, we showed this identity a while ago. Okay, and that's effectively what this is also saying. This phase kickback is basically saying exactly what this is saying over here. Okay, because if you look now, what we've done is we have used, as I said, the target qubit has been controlling, in some sense, the phase that's on the control qubit through this operation. These two statements are equivalent. Okay. All right. So I'm out of time. So what I'll do is I'll upload the notebook. Hopefully you guys can see it this time. And you can play with the balanced oracles on your own. And in the next class, we'll use this identity and understand how to solve Simon's algorithm or Simon's problem. This is a little bit more advanced version compared to the Deutsch problem. Okay. Oh, any questions about this? Yeah.
For me, I can say after. But we go over the -0, -1.
Sure.
Why the minus is in the left head? Or in the left qubit, I mean, like why it's the answer?
So if I just started with minus, that's because I flipped this qubit, the left qubit, right? This is the left qubit. I keep saying right. Correct. Okay. Correct. The left qubit is flipped to to the 1 state, and then a Hadamard is applied.
No, I know where it comes from at the beginning.
Yeah.
Like at the very end.
This part here,
Yeah, like.
Oh,
It's,
I just erased it, but basically this is from the action of X acting on the minus.
no, I think we're still missing.
Okay,
All right,
okay, all right, yeah, we'll talk. Let me just unwind all this. It's an operation each time to get everything set.